Hi, and welcome to the video. Here we're going to have a look at how we can use NSP or Net Sentence Prediction to train a BERT model. Now, in a previous video, I covered how NSP works, but I didn't really cover how you actually train a model using it. So that's what we're going to do here. So we're going to jump straight into it, and we have this notebook. Here is the data that we're going to be using. I will load that in a moment. But first thing I want to do before doing that is import and initialize everything we need. So obviously when we are downloading that data, I'm going to be using requests for that. So I'm going to import requests. And for our actual training of the model, we're going to be using both Hugging Face's transformers and PyTorch. So I need to import transformers. And I'm going to import a BERT tokenizer class and also a BERT for next sentence prediction class. So BERT for next sentence prediction. And as well as that, we need to import Torch. So once we've imported all those, we can initialize our tokenizer and model. So tokenizer equals BERT tokenizer from pre-trained. And we're going to be using BERT based uncased for this example. Obviously, you can use another BERT model if you'd like. So I'm going to copy that and initialize our model as well. Okay. And we can run that. And now let's extract this data. So this warning here, we don't need to worry about that. That's just saying if you are using this model for inference, you shouldn't, because you need to train it a little bit. So we don't need to worry about that. It's fine, because we are going to be training. Now, what we do need to do is get this data. So new data equals requests.get, and we just take this link. I will keep this link in the description for you, so you can just copy it across if you want to follow along. And we should see that we get a 200 response there. That's good. So all we need to do is extract the text from that, and we're going to store it in another variable here, text variable. And if we just have a quick look at what we have in there, we see that we have all of these paragraphs. This is from the Meditations by Marcus Aurelius. You can get that book online. That's why I'm using it. And the language is a bit unique as well. So that's why I want to use it, because when we're using net sentence prediction, we're training the BERT model to better comprehend the style of language that we train it on. So in here, we have our paragraphs, and they're all separated by a new line character. So I'm just going to add another little bit of code here, which is a split by new line character. And we have a look here, we now have a list containing paragraphs, and that's our training data. That's what we want to be using. So when we're using NSP, we want to create a 50-50 split of sentences that are random and sentences that are not random. So we're going to be taking sentence A's, and 50% of the time we're going to be adding the genuine sentence B for that sentence A, e.g. the sentence that follows it in the text. And then the other 50% of the time we're going to be just choosing a random sentence and pulling that in and using that. So to do that, we first want a bag of sentences to actually pull that text from. So the reason we can't just use text directly is because if we, for example, look at this, we see that we have multiple sentences in this single paragraph. So I just split by period, we get, what's this, 1, 2, 3, 4. So we get 4 sentences and this empty one at the end as well, which we need to remove. So what I'm going to do is loop through our text here, so the text variable, split every sentence by the period characters, and append all of those to a new list, so a flat list containing just sentences, so no paragraphs, just sentences. And at the same time, we'll need to make sure we don't include these empty ones, because we get those with almost, I think, actually every paragraph in there. So we need to make sure we don't include those. Now, to create this bag, we write something like this. So we want to go through each sentence. So we want each sentence from each paragraph. So sentence for each paragraph in the text. For the sentences, so for sentence in, so this is where we're getting sentences from. So paragraph dot split. We split by the period. And as well as that, we also need to add that condition that we don't want any sentences that look like this. So we just add that in. So if sentence is not equal to, well, that. And that should be okay. So let's check the length. Okay, so we get 1,372 sentences from that. And we'll actually want to save this to a parameter because we're using it later. So we now have the 1,300 sentences to sample from. And now what we want to do is loop through each sentence within text, or each paragraph within text, choose a sentence from each paragraph, if there's multiple paragraphs only, multiple sentences only, and then 50% of the time select a random sentence from a bag and append that to the end. 50% of the time append the actual genuine next sentence onto it. And then we create labels as to whether we have randomized it or not randomized it. So to create that random 50%, we import the random library, and we also want to initialize our sentence A list, sentence B list, and we also need to initialize a label list. Okay, so that'll be 0 or 1. Now what we want to do is loop through each paragraph in our text. So for paragraph in text, and then here we extract our sentences like we did with the bag before. So we go sentences equals, and here we want to write sentence for sentence in paragraph dot split. And remember, we have those random empty sentences. We don't want to include those. So we write if sentence is not equal to that empty sentence. So we're now looping through each paragraph, and we've split each paragraph into sentences. Now what we want to do is check if that paragraph, e.g. our new sentences variable, has more than one sentence. So we'll do number of sentences equals to length of sentences. And then we say if number of sentences is greater than 1, okay, don't execute it right now. And then we apply our 50-50 logic and append that to our actual training data. Otherwise, if it's just a single sentence, we don't actually add it to the training data. I mean, ideally, we would want to do something like that, but for this use case, I don't want to make things too complicated. So the reason that I'm doing that is, for example, this sentence, it's just a single sentence in that paragraph, and we can't guarantee that each continuous paragraph is talking about the same subject. You might switch. So for the sake of simplicity, I'm just going to ignore the single sentence paragraphs, although we do have them in our bag, so they can be pulled in as potential sentence Bs when we randomize the selection. Now what we want to do is set the sentence that we will start from. So we write start equals random randint. So this is only if we have more than one sentence, remember. So our random randint, so this is going to be the start sentence, In the case that we use sentence A and B consecutively, so we don't randomize sentence B, we want to make sure that we have enough space at the end of our sentences, so here, to take both sentence A and sentence B. So let's say, for example, we have, I'm going to use an example here, so we have 0, 1, 2, 3, 4. Let's say this is our paragraph. We have 5 sentences in here. We want the start sentence, so sentence A. If we select 4, then we don't have a sentence B to select from. So what we're going to do here is say you choose a random integer between 0 and we want 3 to be the maximum there. Okay. So how do we do that? Okay, we've got the number of sentences here, so this value will be 5 in this case. So we would say number of sentences is 5 minus 2, because the maximum value we want to select is 3 in this case. So it's going to be the number of sentences minus 2. Okay. Now what we do is we do our 50-50 randomize or not randomize for sentence B. So if random.random, so this will just select a random float between values 0 and 1. If that is greater than 0.5, then let's say we'll make this our random selection. Okay, so for the random selection, what we do is sentence B dot append, and then here we would append a random sentence from our bag up here. So to do that, we will just write bag, and then in here we need to select a random integer like we did up here. Okay, so we're going to use that same function. So random.randint, and that needs to be between 0 and the length of our bag minus 1. So we use bag size. That's why we have it. So bag size minus 1. Okay, and that will select a random sentence B from that bag for us. And as well as that, we also want to set the label. So our label in this case would be a 1. So we have the 0, which means it is the next sentence. We have a 1, which means it is not the next sentence. So we set 1. Now, our sentence A gets selected. It's the same thing no matter whether we have the random sentence B or the not random sentence B. So we can actually write our sentence A append up here. And this is just going to be sentences. And in the index, we have start, which is our value from here. Okay. So we have the random option. Now let's do our not random option. So in here we'd write sentence B append, and this needs to append sentences start plus 1. So the following sentence after our sentence A. And our label here would be 0, which means it is the next sentence. So it's quite a lot of code. Let's run that and see what we get. Okay. Now, what I want to do is let's have a look at the first few labels, see if we have a mix of different ones in there. Okay, we just have 1, 1, 1, so I'm going to rerun this because I want to show you the difference between zeros and ones here. Okay, so we have these. So let me print out what we have. So for I in range 3, so I'm just doing this so we can print and see what we actually have in our training data. So I want to print the label at that index, and then I want to print the sentence A at that index, and we'll follow that with a new line character and a few dashes so we can distinguish between the start and end of sentence A and B, and then we will do print sentence B. And then I'm just going to add another new line there to distinguish it from the next set of answers. So see here that we have 0, we have our sentence A, and our sentence B is a continuation of that first sentence because we have that label 0. We know that. So we have sentence A here, and again, this one here is a continuation of this sentence A. And then down here we have a 1, so this is where we've selected a random sentence B. And if we read this, I know it's not the easiest thing to read. Yeah, the difference, there's a reasonably clear difference in the context there. Okay, now this won't always work. In some cases, we might select even the same sentence for sentence A and B. But for what we're doing here, I think this is a completely reasonable way of going about it, because we don't want to overcomplicate things. If we wanted to really be very strict on it, we could add in some extra logic which confirms that we are not getting a sentence B from around the same area as sentence A, for example. But for now, this is, I think, fine. Okay, so we've now prepared our data. What we need to do now is tokenize it. So to tokenize our data, we're just going to use a tokenizer, which we've already initialized. And in here, we can actually just pass our sentence A and sentence B like this, and our tokenizer will deal with how to fit both of those together for us. So that's pretty useful. We're going to be using PyTorch, so we want to return tensors PT. And as well as that, we need to truncate or pad each one of those sequences to a maximum length of 512. And then we truncate using this, and we also set padding equal to max length. Okay, so that should be okay. Let's have a look at what we have. We see that we have input IDs, token type IDs, and attention mask. Let's have a look at what they look like. So you see here we have all of these different vectors, and that is a single pair of sentence A and sentence B. And we have quite a few of those. Now, our token type IDs, what we would expect is sentence A would have a token type ID of 0, and sentence B would have a token type ID of 1. But we don't see those ones in there. So let's expand that out a little bit. So we'll go with token type IDs. Let's go with number 0. Okay, so now we see, okay, the reason is because they're in the middle here. So what we're seeing here is sentence A, followed by sentence B, and then these remaining 0 tokens are our padding tokens. So we can also see that if we switch across to input IDs, we'll see that we have all these padding tokens. And as well, another thing that the tokenizer does for us automatically is adds a separator token in the middle of our sentence A and B. So it says sentence A is this, sentence B is this. Okay. So we have our input tensors. We also need to build our labels tensor. And to do that, we add it to this inputs variable. So we have inputs labels, and we set that equal to torch long tensor. And this is a little bit different. So let me just expand that out. So let's say we just add labels in here. So sorry, it's label. And we just get this one big tensor, which is not really in the correct format that we need. We need each one of these to match to our input IDs, token type IDs, and attention mask. So what I mean by that is if we just have a look at this, input IDs, you see that we get, it's like a list within a list. We need that, but for our labels as well. They're in a different format at the moment, as you can see. So we could try transposing that, but you see that doesn't actually do anything because it's just a single dimension, so it's just switching everything around. So let's remove that transpose and let's add a list inside here. You see now we're getting somewhere, not quite there yet. So now we have a list within a list, and now what we do is we transpose it, and now we get what we need. So we have this almost vector of each of these, and each one of these here, so this vector matches up to this value here, and this one matches up to this one, and that's what we want. So let's copy that and we'll put it here. So now we have all of the tensors we need for training our model, and what we now need to do is set up the input pipeline for training. So when we're training, we're going to need to use a PyTorch data loader object, and to create that data loader object, we need to create a PyTorch dataset object from our data. So to do that, we write this. So we're going to be using a dataset class here. So I'm going to call it meditations dataset. And in here we write torch utils data dataset. So that makes sure that we are using the correct format for the class for a dataset. Now we need to define a few methods inside here. So our initialization method, and for our initialization method, we need to be able to pass our data. So we'll pass it through this encodings variable. And all we need to do in here is assign our encodings variable to be an internal attribute of that data set or that class. So write self encodings equals encodings. So that allows us to create our dataset class. And then our data loader needs two different methods from this class as well. It needs a getItem method and a length method. So let's do the length method first, it's easier. So our length, we don't need to pass anything to this. It's just, it's the same as when you would write, say you write this and you put something inside it. So a list 01, and we get that length. That's exactly what we're doing here. So this creates enables you to do this same method on your class. And inside here, all we need to do is return the length. So what length should we return? Well, if we just do len of inputs, we get 4 because we only have 4 items in there. So we don't want that. We actually want the number of samples that we have within our inputs. So what we can do instead is we write inputs, input IDs, shape 0. So we have this 317 items. So just to show you here, see this is our encoding size. So the max length we set here, and this is the number of sentences or sentence pairs that we have. So we take that and we return it, but obviously we don't have inputs. We now have this self encodings. So swap it like that. And then we want to pass this getItem method. And what this does is, given a certain index, it will return your 4 dictionaries, your input IDs, token type IDs, attention mask, and labels dictionary, which we created down here, for that specific index. So we need to allow it to take an index argument there. What we do is return, let me show you down here what that would look like. So we want to create a dictionary just like we have up here, but we just want that for that specific index. So what we write is key, and then we write our value index. So maybe it makes more sense for me to write so tensor. So our key is our input IDs, attention, mask, and so on. Our tensor is obviously the tensor inside there, but we have the full tensor containing all 317 items. So then we pull out the index for that tensor, but we need to make sure we're doing that for each of our items. So because we have multiple tensors here, don't we? We have the 4 input IDs, labels, and so on. So we do for key and tensor in, and in here we would write, let's say I'm going to do inputs items. So let me just take that out so you can see. So that gives us our dictionary items. And if we do a for loop, so for key tensor in, we want to print, let's print the key, right? So you see that we're looping through each one of those. And we also get the tensor out for each one of those as well. But we're specifying a certain tensor with each one. So let's say we want 0 here. We would get the 0th tensor and nothing more. Okay, but we want to specify an index, so we copy that, and it's what we're going to return here. Except here, we change it to self encodings. So that's our class. And with that, we can initialize our dataset object. So we'll say dataset equals meditations dataset. And then all we need to do is pass our data, which is, sorry, it's just inputs here. Like that. Okay, so that's our dataset ready. Now we can initialize our data loader. And we do that like this. So we do loader torch utils data.data loader. We pass our dataset object. We also want to specify the batch size, so I'm going to use batches of 16. And then we also want to shuffle our dataset as well. So we write shuffle equals true. And that's our data loader. So now we just need to set up a few model training parameters. So the first thing we want to do is move our model to a GPU if we have a GPU. So to figure that out, what we do is write, let me do this, torch device CUDA. So this is, we say we want to use a CUDA enabled GPU. If torch.CUDA is available. So this will check our environment and check if we have a CUDA enabled GPU. If it isn't available, we want to use a torch device CPU. Let's run that and see, for me, I have a CUDA enabled GPU, so it comes up with this. So we saw that in device. And then what we can do is move our model and also move our tensors later on to that device for training. So we just write model to device. And we'll get a lot of output from that. We just ignore that. We don't need to worry about it. And we can also activate our model's training mode like that. Okay, so we've moved our model over to a GPU, activated training mode. Now what we need to do is initialize our optimizer. So we're going to be using Adam with weighted decay for our optimizer. So to use that, we need to import it from transformers. So from transformers, import AdamW, and we initialize the optimizer like this. So we item w, we pass our model parameters, and we also want to pass the learning rate, which is going to be 5e to the minus 5. Okay, that's a pretty common one for training transformers. And that looks pretty good to me. So now we can begin our training loop. So first, I want to import something called TQDM. Now, this is purely for aesthetics. We don't need it for training. This is so that we see a little progress bar during training. Otherwise, we don't see anything. So I just want to include that so we can actually see what is going on. So from TQDM, import TQDM. So this is optional. You don't need to include it. It's up to you. But I would recommend it. We'll train for, let's go with 2 epochs. Again, we don't want to train transform models too much because they will easily overfit. And to be honest, they'll probably overfit on this dataset because it's very small. But that's fine. We just want to use this as an example. So we're going to train for 2 epochs. And because we're using TQDM, we want to set up our training loop like this. So we wrap it within a TQDM instance. And all we do here is pass our data loader. So we create that up here. That's our PyTorch data loader. And we also want to write leave equals true. So this is so that we can see the progress bar. And then we loop through each batch that will be generated by that loop generator. So for batch in loop. So now we're in our training loop. What we want to do here, very first thing, is set our optimizer's gradients to 0. So obviously in the very first loop, that it's fine, it doesn't matter. But every loop after that, our optimizer will have a set of gradients that have been calculated from the previous loop, and we need to reset those. So we write optim 0 grad, and after that, we can load in our batches or our tensors from our batch here. So we want input IDs equals a batch, and we access it like a dictionary. So we have input IDs. So input IDs. And one other thing that we need to do is our model is on our GPU. So we need to move the data that we're training on to our GPU as well. So we just write that. Okay. And copy this. So we have one more. So we have all of these that we create up here. So input IDs, token type IDs, attention mask, and labels. We want all of those. So token type IDs, attention mask, and labels. Okay, so initialize our gradients. We have pulled in our tensors, and now we can process them through our model. So we do model, input IDs. We have token type IDs. We also have the attention mask. And we also have our labels. Okay. So that will create 2 tensors for us in the outputs. It will create a logits tensor, which is our prediction, and it will create a loss tensor, which is the difference between our prediction and our labels. So let's extract that loss. So we do outputs.loss. And then we also, after extracting that loss, we need to calculate this is the overall loss. We need to calculate the loss for every parameter within our model so we can optimize on that. So we just write loss backward. I think it's, yeah, backward. And then we do optim step. And this will use our optimizer and take a step to optimize based on the loss that we've calculated here. And that is all we actually need for our training loop. We do also have the TQDM up here as well. So I just want to use that. And what we're going to do is we're just going to set the description of our loop at this current step equal to the epoch. So this is just purely aesthetics. We don't need this for training, but it's just so we can see what is going on. And we also want to loop set postfix. And here I'm going to add in our loss, which is just going to be loss equals loss dot item, like that. Now that should be okay. Let's give it a go. Let's see what happens. Okay, so that looks pretty good. So you can see that our model is training, loss is reducing. Now there isn't that much training data, so we're not going to see anything crazy here, but we can see that it is moving in the right direction. So that's pretty good. So that's everything for this video. It's a pretty long video. I've recorded for 41 minutes. It'll probably be a little bit short for you, but yeah, that's long. So that's everything for this video. I hope it's been useful, and I will see you in the next one.